So this I will change the color here.
So you can select, there are several colors.
Yes, several colors here.
Green, blue, pink, yellow,
Take this.
orange. So you can take any
How
one.
is this color? This is good.
Dark.
This is blue. This is dark blue, no?
Yes.
So I think this is fine. So there is
Yes, sir.
this is different. Okay. So shall we start? Okay. So good evening, welcome. And today is going to be my last lecture. We covered in the last few lectures the practical aspects of NMR spectroscopy, how to obtain good spectra. Then we also looked in the last lecture a few examples how to analyze the spectra. Some complicated organic molecules which has a large number of resonances, larger number of protons, and the stereochemistries are quite complicated. How to analyze this, how to get this complicated stereochemistry. And it is based on the application of three techniques which we demonstrated: the double quantum filtered COSY, the TOCSY, and the NOSY, with the proper connections in each case. We also looked at heteronuclear experiments, HSQC TOCSY, HSQC NOSY, how we can use this to identify individual connections in complicated organic molecules. Now we are going to continue that sort of an exercise with peptides and amino acids. The peptides, of course, are small, are reasonably small molecules, of course, larger than the conventional organic molecules. And of course, the proteins are much larger molecules, and this will actually, we will take it up the next module of the NMR course. We are going to look at today the application to peptides. And one difference with regard to other kinds of organic molecules which you saw was, we already know what sort of amino acids are there in peptides. The peptides structures are known, amino acid structures are known. So then we can expect what to get in our NMR spectra. So because the structures of these amino acids are known, there are 20 different types of amino acids. The structures of individual amino acids are known. So what you expect in the COSY spectrum, or the double quantum filtered COSY spectrum, or the NOSY spectrum is what is one has to know. And that is what we are going to do now. So let us start from the very basics here with amino acids. Amino acids are indicated here. This is the basic structure of an amino acid. Here you have the NH2 group and the C alpha. This is C alpha. This is C alpha. Then you have the side chain labeled as R1. Then you have the proton there, C alpha proton. Then the carboxylic acid group. Now the R1 group can vary. That is the one which varies among the 20 different amino acids. So you have now, if you connect two such amino acids adjacent to one another, taking away a water molecule in between, then you get a peptide. So you form a peptide bond here. This is the peptide bond, and that is the NHCO. This is the peptide bond here. This is a dipeptide, so to say. Then you have, so therefore here you have combined two amino acids, R1 and R2, and by making a reaction here. So you remove one water molecule, then you generate a peptide bond which has a planar geometry. So this bond, the NC bond here, is a double bond character here, and because of that, this is the planar geometry. There is no free rotation around this. The free rotations are there around this particular bond, and the side chain bonds here. So you have free rotations in the individual amino acids. So that generates a whole varieties of different kinds of structures. The structures of the side chains here, the R1 and the R2, which are there, and these are indicated here. So there are different kinds of amino acids, as we can see in this. There are certain neutral amino acids. The neutral amino acids are alanine, asparagine, cysteine, glutamine, glycine, isoleucine, leucine, methionine, phenylalanine, proline, serine, threonine, tryptophan, tyrosine, valine. Now notice one thing, that of course all of these are L amino acids. There can also be D amino acids in principle, in general. However, this is the stereochemistry, but nature has somehow chosen the L amino acids in the construction of the proteins. So if you put a D amino acid somewhere in between, this is the stereochemistry. The nomenclature, chemists will know these nomenclatures. So what this L and D means. So don't confuse with the small L and small d. That is a different thing. And these are capital L and capital D, but in the nature we have capital L amino acids. All of them are in this manner. Then you have so many neutral amino acids. Among these, some have aromatic rings. The aromatic rings ones are like phenylalanine, then you have tryptophan, the tyrosine, and these have aromatic rings. And then you also have histidine. Histidine is, of course, aromatic, but it also has nitrogen groups in between. So the histidine is listed here or no? Where is
Yes,
this?
basic amino acid.
It's listed on the basic amino acids there. Histidine is here, yeah. So it also has this, it was the NH2 nitrogen say that which comes under the basic amino acid groups. Acidic groups are this aspartic acid, L-aspartate, then that's the only one. Actually, there is glutamate also, glutamic acid, yeah, here. Glutamate and aspartate, these are the two acidic amino acids. The basic amino acids are three here, arginine, histidine, and lysine. So these ones are basic amino acids. We have two acidic amino acids and all others are neutral. However, they also have OH groups and carboxyl groups. Then, so for example, here you have a COOH here, L-tryptophan. But then, of course, when you form a bond, of course, this carboxyl group doesn't remain as a carboxyl group. This remains as a CO bond there in the peptide groups. So in all of these, this OH group is removed. Then you also only have the CO when you form the peptide bond. So threonine has a hydroxyl group on the side chain. Serine also has a hydroxyl group on the side chain. So these are polar amino acids. So you can classify these amino acids as polar and non-polar as well. There are many residues which are polar. Those are hydroxyl groups, they can be considered as polar. Okay, I mean this, for example, are you also have a tyrosine. A tyrosine in the side chain has an OH group. Here, tyrosine in the side chain has an OH group. So it can be considered as an aromatic ring, but also a polar group, because the OH group is there. So, and the basic amino acids are because of the nitrogen, NH2 group, they get protonated, and of course you can get NH3 plus there and things like that. So that will cause a change in the structure of the molecule, depending upon the pH and the pK of the peptide. So you will have different kinds of configuration, different kind of charged states of the individual amino acids. The neutral amino acids, of course, will remain neutral. Okay. Then there is also the cysteine, which has the SH group in the side chain. The SH group can actually form disulfide bridges. SS disulfide bridges it can form. That actually provides a covalent linkage between two cysteine groups, and that can also significantly influence the structure of the peptide or the proteins. Okay, so now we know all of these individual structures of the amino acids. Then we have to also calculate what these structures result in the NMR spectrum. Okay, so here you have the peptide formation indicated in this here. So you have the one amino acid, another amino acid here. So you have the HOH being removed. This is removed here. These two gets removed, and then you have the peptide bond formed here. This is the so-called peptide bond, which is planar in nature, because the double bond character of this CN bond, there is a double bond character, so there is no free rotation around that. Typically, these NH and CO are trans in orientation. That is the most stable configuration. Sometimes you may also have a cis configuration, but that is very, very, very less. So that is more, there's higher energy compared to the trans configuration. Therefore, you will, by and large, you will have the trans amino acids, trans peptide groups. So this has the hydroxyl, there is, in other words, the torsion angle, if you talk about, this will be 180 degrees with regard to NHC double bond O. Then your geometry of the peptide will be determined by the torsion angles, which are connecting C to the CDO and C to C carbonyl and nitrogen to the C alpha. So these torsion angles determine the geometry of the backbone of the peptide backbone. So we have to identify the individual structures of the amino acids, and we have to use standard methods of COSY, NOSY, TOXY, and all of those ones. Okay, so what kind of structures we form for the peptides? So if you have polypeptides, the primary structure is the sequence of the amino acids. Which amino acids you can determine, though there are biochemical methods to determine the sequence of the amino acids in a given peptide or a protein. Then you can have secondary structures. There are certain kind of structures they can form, which are called as alpha helices or the beta sheets. Here Then you have the third, at the higher level, at the next level of structure, then you have the folding of these individual things. It forms a so-called tertiary structure. And then you have the quaternary structure where these folded tertiary structures assemble to form a more complex organization structure, and that is called as a quaternary structure. So the structures are at different levels. By and large, the peptides, we don't come in at this level, but mostly we will be dealing with at this stage. When you are talking about peptides, they don't have such very complex structures. Okay, so now to give a little bit more info into the structures, what kind of structures they can form. As I said, the torsion angles which determine the structure of the peptide or the structure of the individual amino acid are two, and those are called as the phi and the psi. For each amino acid, there are two torsion angles, phi and psi, phi and psi. So therefore, if we have, that means 2 degrees of freedom with respect to each amino acids. So if they have a 10 amino acids, then it will be 2 to the power 10 degrees of freedom. But then of course, all of them will not be allowed, and that is determined by what is called as the Ramachandran map. In the structures, what kind of phi and psi are allowed, and that determines what sort of a secondary structure the peptide can have. So typically, certain combination of phi and psi will lead to what is called as the helix. This is the alpha helix here. And a certain combination of phi and psi will lead to a beta sheet. This is a beta sheet structure. And of course, you can have combinations. The tertiary structure will involve some portion in the alpha helix and some portion in the beta sheet, or you can have only helices, or you can have only beta sheets. All these kind of structures are possible in the peptides. Now, the peptides will take various kinds of turns. So there are two different kinds of turns which are described here. So when you go from one amino acid to the another amino acid residue, we talk about residues now. When you talk about the peptide, each amino acid is called as the residue. There is a residue 1, residue 2, residue 3, and so on and so forth. So here what we have shown is there's a stretch of certain amino acid residues. Considering a dipeptide here, I plus 1 and I plus 2, this is I and this is I plus 3, a 4 amino acid stretch if you take, what kind of turns they can have around this particular one. There are two types of turns which are described here. You go from here, this is alpha, NH, C alpha, CO, NH, C alpha, CO, NH, C alpha, it continues that way. So in this particular case, the central portion here, this particular stretch, if you see, therefore, here you have the CO and the NH, they are going completely in one direction. CO is going here, NH is going in the other direction. This is called as the type 1 beta turn. And then you have, in this case, the CO goes outside and the NH comes inside. And this is called as a type 2 beta turn. Okay, what determines this? These are determined by the torsion angles. The phi and the psi torsion angle combinations will actually determine what sort of a orientation the individual, these groups will have. So therefore, we represent as phi I plus 1, psi I plus 1, phi I plus 2, psi I plus 2. And these are reflected, you can measure this kind of structures on the basis of certain parameters like the distances. For example, if you have this sort of a structure, then you have the distance between this C alpha and this C alpha here will be approximately 7 angstroms. So these are standard structures known, and these are the units which will occur in the peptide structures or the protein structures which will happen. Okay, so and then here you have a beta sheet where what is the look at the beta sheet, what sort of a beta sheet it is? You have the NH, C alpha, CO, NH, C alpha, CO. Okay, in the second one, if you see, this is running in this manner, NH, CO. So it is chain is running in the opposite direction here. NH, C alpha, CO, NH, C alpha, CO, NH, C alpha, CO. So that these two chains which are held together by hydrogen bonds here, NHO and NHO and NHO here, these two chains are running in opposite directions. So that is why it is called as an anti-parallel beta sheet. But you can also have parallel beta sheets where the two chains run in the same sense, and then it will be called as a parallel beta sheet. Okay, so that much of introduction with regard to the structural properties of the peptides. What sort of a structures you can expect in those. Now, what does the NMR spectrum of a peptide look like? Okay, this is a typical one-dimensional spectrum. Here you have the proton spectrum here, and it is a well-folded, reasonably well-folded peptide. Therefore, you can see that the chemical shift distribution is quite high, quite good. But certain areas you can identify as on the basis of the chemical shifts, on the basis of the structures. You can say all the methyls will appear in these areas, high chemical shift. I mean, the ppms are low, between around 1 ppm. The entire aliphatic area appears up to 3 ppm there. So this is Then you have the H-alphas. The H-alpha is in the middle of the amino acid. The H-alpha appears here between 3.5 to 5.5 and 6. Then you will have the side chain here and the aromatic ones. The side chain NHs will appear in this area from 6 to 7.58, sometimes a little more than that. Aromatics will appear from 7.7 ppm up to 8 ppm. Then the backbone NHs appear quite a wide range of chemical shifts. There you have all the way from 7 ppm to 10.5 ppm. Side chains of tryptophans will appear here. This is something very special. These are the tryptophan side chains. So the indole ring of the tryptophan side chain will produce peak at this around 10 ppm. So these are typical chemical shift ranges we have for the amino acids. for all amino acids, these are common. The aliphatic, and what determines the dispersion of this? The dispersion of these ones will depend upon the environment or the kind of a secondary structural fold or the structural fold the peptide might take. Whether it is helix or the beta sheet or whatever combination of those ones, then there can be distribution of the chemical shifts. In other words, if you take a particular amino acid residue, let us say serine, the serine can have more than one chemical shifts. It is not that serine will have only one chemical shift. Serine in one environment has one chemical shift, serine in another environment has another chemical shift. So therefore, that is what leads to a great distribution of chemical shifts in this. The amide proton chemical shift produces the maximum dispersion. Therefore, most of the experiments which we use, you will see later, that will exploit the NH chemical shifts quite extensively. Okay, now here I indicated the structures of the individual amino acids once more, along with the nomenclature and the full details of the side chains. So you have this is the proline. The proline is a closed ring. The side chain of proline actually NH it folds onto itself. You see, the proline does not have a NH group. So that is something which is a sequence breaking kind of thing when you are talking about the connectivities in the peptide structure. See, proline doesn't have an NH proton. And so these are all alpha amino acids. Okay, these are called as alpha amino acids. And we have the C alpha is here. And on the nomenclature goes into the side chain, alpha, beta, gamma, delta, and so on and so forth. Okay, the side chains are going like this. Alanine, for example, has a methyl in the side chain. It is called as the beta methyl, because it is present in the beta position. It is a methyl group, it's present in beta position. If you go to arginine, then you will see the side chain goes all the way, beta, gamma, delta, epsilon, and then you will have these other NHs over there, which are exchanging. These are NH protons. Okay, sometimes they will also be charged. These are basic. They can be positive charge there. The asparagine has the CONH2 group, and this goes from beta to gamma. At the gamma, it has the CO group, and then the NH2. You have these amino acids. These NH2 protons will appear actually as two separate lines in case there is a structure, because then these two protons will become non-equivalent. Delta 2,1 and delta 2,2, these will become non-equivalent. And if you aspartate, it is the carboxylic group in the side chain, and therefore you will have the CO and OH there, and beta gamma. So it goes up to the beta gamma. The cysteine is beta gamma, and the gamma position it has as the sulfur. Glutamine has C beta, C gamma, C delta. At the C delta, it has the CONH2 group. CONH2 group, just like the asparagine. Asparagine it has at the gamma position. In glutamine, it is at the delta position. Okay, and glutamate, it is an acidic group here. It also has the COOH. Like the aspartate is the C beta, C gamma. At the delta position, you have the carboxylic group. Histidine is a closed ring here. It has two nitrogens in the side chain, and this makes it a basic one. Histidine is a very important amino acids in the proteins. It has a pK value something like about between around 6 or so. So its pK can change depending upon the environment. Therefore, it can be charged or otherwise depending upon the pH of your solution. And in many situations, even at neutral pH, some of the histidines may be charged. That depends on the local environment in the protein structure or the peptide structure. And that is there, these nitrogens here can get protonated. And that will have a charge distribution, will change it, then can change the repulsions. And there are many important proteins where you see histidine, the repulsions of the side chains drives the structure of the protein. Then isoleucine, these are methyl bearing groups. So isoleucine has one methyl, this is the beta, gamma, delta, and the delta there is a methyl group there. Leucine has two methyl groups. C delta 1 and delta 2. These are two methyl groups there. C beta, C gamma, C delta, and 1 and delta 2. These are two methyl groups there. Lysine is again a long side chain, beta, gamma, delta, epsilon, and the epsilon position it has a NH2 and an NH2 group, and of course that can become NH protonated. Methionine also has a sulfur. Unlike and just like the cysteine, it has a sulfur, but then this sulfur is attached to a CH3 group. It is not SH group. Cysteine has a SH group, and the SH group leads to the disulfide bond formation. Methionine cannot bond form disulfides. It has a SCH3 group. Therefore, the S is occupied there, and you cannot form that. Phenylalanine, this is an aromatic one. You have a ring there, and all of this, the beta, gamma, beta, the beta group, and this gamma. The serine has a OH group in the side chain at the beta position. Threonine has a beta gamma, and then of course it has a OH again at the beta position, CHOH it is. So, and then you have tryptophan, this is the indole ring here, and that produces the distinct amino acid. Many times this NH group here, which is present in the side chain here, this appears at around 10 ppm, so it is uniquely identifiable tryptophan side chain. And this tyrosine is an OH group in the side chain here. So this is the polar one. So this makes, many times it forms hydrogen bonding contacts. The valine again has two methyl groups at the gamma position. Gamma 1 and gamma 2, these are two methyl groups. So therefore you see, we have we know the structures of the individual amino acids. Therefore we also know what to expect in our 2D spectra. Okay, this is what happens in the 2D spectra. So these are the chemical shift ranges of the individual amino acids there. So the alanine has only one beta, therefore it has an alpha beta in this area, and cysteine has alpha beta here, aspartate has alpha beta here. This is the chemical shift ranges that given at the bottom there. Typically all the alphas appear between 4.5 to 5.5 ppm, and all the alphas are here, and all betas are here. And then you see, except with the beta of the alanine, which is very distinct. The beta of alanine is distinct, therefore it is easily identifiable. Okay, and in this area, of course, there is quite a crowding. Beta, gammas, and the deltas of the various long chain amino acids, they will all appear in this area. Beta, gamma, delta 1, delta 2, beta, gamma, beta, gamma, delta. And of course, the lysine has a epsilon proton, which appears also quite distinctly here in this area, around 3 ppm. Arginine also produces this things in that ppm around that area. These are the amino groups. Okay, so these are not the non-exchangeable protons; these are exchangeable protons. They appear in this area. And now, depending upon how you record the spectra, whether you record the spectra in D2O or H2O. If you record the spectra in D2O, all the NH2s and the NH protons may not appear. They will be deuterated. You will not see them. Only the non-exchangeable protons will appear. If you record the spectrum in H2O, then your exchangeable protons also will appear. So all the side chains which have the NH2s and the NH3s and all of those, they will also appear in the spectrum. So the methyls are typically in this area. The betas are around 3 ppm. Aromatic ones have the betas around 3 ppm, and all other aliphatic betas appear between the 2 to 2.5 ppm. Okay, so these are typical ranges of the chemical shifts, and you can see that in a typical 2D spectrum which I've shown you here. So this is in the 2D spectrum how they will appear. So you see here H alpha, this region is the alpha area, alpha beta area. This is the amide proton area, 7.8 ppm to 8.6 ppm. This is a particular region which is shown. Doesn't matter which peptide this is taken from, but you can see here there is this crowding of the peaks in this area. These all belong to the alpha. NH to the alpha protons. And what is present here, it all belongs to the beta protons. The beta, gamma, delta, and the methyls. It all belongs here. So this region will be generally very crowded because there are many amino acids, many protons which give rise to chemical shifts here, as you can see from here. See, there are so many things which are present in this here. This is the same area, 1 ppm to 2 ppm area. So all of these peaks will appear in this area. And this area is clean. This is only alphas. So on this which are present here, these are only alphas, only alpha proton. Therefore, often you make use of the alpha protons to obtain sequence-specific resonance assignments in the proteins. And after that, you make alpha-beta connections and things like that. Alpha-beta, beta-gamma connections in the toxic spectrum and the double quantum filtered Cauchy spectrum. Okay, these are general characteristics of the spectrum. Okay, now you see, if you have a typical peptide, the Cauchy spectrum, how does it look like? See, certain areas are very distinct. And in the COSY spectrum, what do we see? We only see J coupling correlations. J coupling correlations exist only within the amino acids, right? There are no couplings between one amino acid to another amino acid. So these are farther, long range, 4 bond and more they are. Therefore, you don't see J coupling correlations in peptides from one residue to another residue. You will see within the same amino acid residue. And since the alphas are all very distinct, these correlations on the NH to the H alpha proton, NH to the H alpha is the 3 bond coupling correlation. So all of those will appear in a very distinct area here, NH to the alpha. Okay, and then of course you will have some things here. These are from the aromatic ones to the beta protons. So you will also see somewhere here some of those ones from the aromatic proton. And these are within the aromatic protons. These peaks are from within the aromatic protons. Tyrosine, phenylalanines, tryptophans, all of them will appear the correlations in this area. So these ones, very distinct area. The most crowded area here is this. This is alpha beta area. This is the aliphatic area. The aliphatic area is alpha to the beta, beta to the gamma, gamma to the delta, and so on and so forth. All of them appear in this area. And often this is the most complex region to analyze. Okay, so therefore proton-proton COSY spectra, often you limit yourself to analysis here, but if this small peptide, easy to analyze this area, you do analyze this area as well. So this is the first thing to analyze. By simply counting the number of peaks here, you can see what sort of what is the kind of how many residues are there in your peptide. So each one will give you one peak because NH to the alpha, this is NH here, this is NH area, right? The NH to the alpha, you can count here the number of peaks. How many peaks are there? That is that many amino acids are there in your peptide. It must correspond to that. Except of course the glycines. Glycines has 2 alpha protons. Okay, all other amino acids has only 1 alpha proton. Glycine has two alpha protons. Therefore, for a glycine, you may see 2 peaks if they are non-equivalent. But they are equivalent, then of course you may see only 1. Okay, and all others are on this area. Okay, so therefore this area is easy to analyze. Okay, now here I show you a little bit more of that one there. So this is again the NH to the C alpha area. This is a particular small peptide. It's in 5 amino acid residues. How many peaks are there? You can count here. 5. Therefore, there are 5 amino acids in this. And of course, all of them have the fine structure. This we have seen before, that all the cross peaks will have a fine structure. But at this point, we are not worrying about the fine structures in the individual cross peaks. We are simply counting the total number of peaks there. So each one of them is 1 peak. The fine structure is which contains the coupling information, but we are not concerned about that at the moment. Now, for the same one, you look at the toxic spectrum. Now, the toxic spectrum produces you, see, what is the way we analyzed here? Here, if you get the alpha protons, to get these other side chains, other protons in the side chain, you have to go from alpha to the beta, beta to the gamma, gamma to the delta, and so forth, right? And this analysis is going to be more complicated. On the other hand, if you go to the toxic spectrum, you will see these correlations with the NH protons itself. The NH protons has a relay. It goes to the relay, alpha to the beta to the gamma and so forth. For example, you look at this particular peak. Which are the 5 peaks here? So these 5 peaks are what are present in the COSY. That is this one, this one, this one, this one, and this one. These are the 5 COSY peaks. Okay, they will appear in the toxy as well. Now, from each one of those, you are seeing other peaks. Now, you see from this one, you see one of them here. It shows only 1 peak. Okay, and therefore it has only 1 side chain other than alpha. Therefore, the alpha to the beta, unless these 2 are equivalent. There are 2 which are equivalent. It can happen there, of course. So the beta 1, beta 2. So this is the 1 beta. Now, if you look at this one here, it shows 2 protons here. Okay, so it is connected to 2 different protons. And what are the chemical shifts there? These are somewhere around, see, you can go here, 302, 2.5 to 7. So what is typically what we will consider here? This may belong to an aromatic one. Because typically beta proton region is between 2.7 to 3.5, the beta chemical shifts. We saw that in the table before. Therefore, we can assume that this may belong to one of the aromatic rings, possibly. Okay, now what you see here, let us look at this. This one, this shows you a peak at this point, and it shows a peak at this point. And there are so many peaks there. What are those? So this will produce peaks to some other in the aliphatic area, and produces a peak here in the alpha area. What is that? See, this is the quite, so this one is quite likely whether there is one amino acid there or two amino acids there, we don't know. Maybe there are two. If they are overlapping there, we don't know. So it has one peak here. It shows a relay to one particular proton here and a relay to two other protons there. That is this one we are talking about. It's showing a relay to one here and it shows the relay to two other ones there. Possibility is that if suppose it is a threonine. See, the threonine beta typically appears very close to the alpha because threonines in the beta has a OH group, CHOH in the beta. So therefore that chemical shift in the beta is quite downfield. It's almost close to the alpha proton. That is one possibility. Other thing will be that, well, so this could be it can be from the side chain of the lysine. The lysine side chain peak, if it is coming, the side chain NH2 is appearing here, it produces a peak to the epsilon of the side chain. Okay, this may not be an NH alpha peak of the side chain peak. It may be an epsilon of NH2 of this lysine, and it shows a peak here, which is coming at the right point from the side chain. And the side chain, it is now showing the toxi here, the relay to the betas and the gammas and the alphas. Okay, so therefore, by looking at this, you can say now, this initially we thought this is an NH3 alpha. H alpha proton is shifted so much downfield, this is rather unlikely. Therefore, what is likely here? This may be a lysine. Okay, a lysine or an arginine. Arginine is also possible. So from here you have the beta proton, which is coming around 3.4 or 3.5 ppm. So this is not a beta proton, this is a epsilon proton. And what is present here is the side chain of lysine. The side chain of lysine is showing a direct correlation to the epsilon proton, and this one is showing a relay to the alpha and to the beta and to the gammas. Okay, and now the other ones you see here, this one is showing correlation to here and here. So this is going into the methyl area. So the methyl area. So this is one, there is one here and one there. So what could be this? On the basis of the chemical shifts, there is a one beta proton here and the methyl there. What could be this? This is very likely a valine. The valine beta appears in this area. Valine has a methyl. Okay, so the methyl therefore appears in this area. It could be valine. I'm just analyzing in front of you, making all kinds of guesses. You will also make similar kinds of guesses when you are actually going to analyze the individual spectra. So similar kind of things which will appear in the different area now. For the same one, the different region is shown. You have to confirm this, but if you can establish connections in this area, establish connections to the alpha to the beta. We said, okay, we have the alpha here and turn to the two betas there. And the two betas, so the alpha to the beta also you should see correlation. So you go to this beta, what is this alpha? This alpha is around 4.2 ppm. So the 4.2, that is this peak here. This is the alpha beta area. Okay, the alpha beta area is showing you these two peaks there. And that is the same which are present here. Okay. So therefore, this establishes the correlation. Alpha beta is clearly there. It is also showing something else there. This is something a little bit more, something else, or it is showing something here which is very weak in the methyl area. Either this relay has not happened completely to this point. This could happen. This could very well happen, and therefore it is limited only to here. But in this area, the relay is happening from the alpha protons. The alpha protons to the betas, and then maybe it is going to the methyl as well, to the beta, subsequently the gammas as well. Therefore, you always have to cross-check what you see here with this here in this. This is also toxic spectrum. This is the toxic spectrum. Here the toxi is from the NH to the alphas and that area, and here is the toxi from the same portion of the spectrum, alpha to the beta to the gammas and things like that. So the relay can happen here much longer than the relay here. The relay here starts from the NH proton, goes up to the betas, and it may not able to reach gammas. But here, when it starts from the alpha, it can go to the beta, it also can go to the gammas. Therefore, you have to cross-check here and here to identify what is the kind of an amino acid there. So, after all, when you completed the analysis, all the peaks must be exhausted. There should be no peak left unassigned. Every peak must be completely assigned. So when you have that, then you have the confidence that, okay, what you have analyzed with the receptor amino acid is correct. Now, this becomes simpler in the sense that you already know what chemical shift ranges you expect. And that's why it becomes relatively easier to analyze that. And now you see here, there is one fellow here, which is a loner. This stands all alone here. What is this one here? What is that one there? That looks like a alanine. So you have the alpha proton here, and then it shows one peak to the beta. Nothing else. Alanine has no other connections. Remember, we are talking about connections within the side chain of the individual amino acid. There are no connections from one residue to another residue. And this is a loner here, which will immediately tell you that this must be a glycine, and this must be an alanine. And because of the methyl is appearing in this area, alpha to the beta, and there's nothing else. Okay, so that is the same area here. So this one, these are both same areas. This is from possibly from the double quantum filtered COSY, and this is from the TOXI. There are no peaks here. Okay, this is the region from the double quantum filtered COSY, and this is the region from no, it's not from the double quantum filtered COSY, is it?
I think this right
It
hand
is.
is TOXI.
Right hand is TOXI, the left one is double quantum filtered COSY. Yeah, DQF COSY. So that is the same thing. The TOXI also, you see, there is only one here. So this is only one peak. This is the alanine beta, alpha to the beta.
And then 4-1C showing more number of peaks. The alpha CH.
This one here, this one here. This one you're talking about?
Yeah. So 4-1. Then
Next one.
Next 4 and 4 PP.
Oh, this one here. Oh, this one is showing many here.
Many here, but here only it is showing 2-1.
Correct.
So this is the DQ question.
There is showing only one here. So it is showing alpha to the beta.
Yeah. And then
This beta is actually quite complicated. You see here, this is quite a spread there. There are possibly more than one betas there. More than one betas, and the two are just close by. And this one you see here, that is the same one. This one we are talking about, that is this peak here. This peak in the TOXI is showing a peak to this one also. This peak here, I have a feeling there are two amino acids there.
Yeah, in one maybe you see.
There is slightly left shifted. It's slightly to the left.
Yes.
So these two are in one line. There is another one. These three are in one line. So they are quite close.
And one methyl is there.
There is one methyl here.
So it must be leucine.
It must be leucine. Yeah, and it has a beta here. Beta gamma, leucine beta gamma also will be around that area. And then you have the methyl area, which can be to the leucine. So, and this one here, these are again only beta 1 and beta 2, alpha to the beta 1 and beta 2, or it could be beta 1 to the gamma 1 and gamma 2. So you come from here, see this connection, you see, you make a line here, this connects here, and this connects to these two. That is the same connection here, these two. What you see in this area, see it stops here, that doesn't go beyond there. So this one is connected to this, but these two are connected to this, and that is connected to this. So therefore, see, you have to analyze this very carefully. So this is one cross peak here. This is from the alpha to the beta to the two gammas there, gamma 1 and gamma 2. Okay, and then this is around the 2 ppm area. Could be the leucines there. And this beta 1 to the beta 2, but this is not showing to the methyls. But this one is showing, one of them is showing to the methyls there. This is not showing to the methyls. So therefore there are two there in that area. And this, there is what is here? These two close by here. This looks like beta 1, beta 2. And that is these two which are present here, this one and this one here. These one is showing cross peak between themselves, beta 1 and beta 2. Okay. So similarly, all those which you see here in this area, the beta gamma cross peaks. You have this one here and another one here. So you see a cross peak between these two. There is so this and this and this. So this cross peak is between these two. So you will be able to analyze, combining all of this input and this input, one can assign the individual peaks quite clearly. So this is looking like a small peptide, but of course it has its complications in it. How many are there? So only when you analyze this in greater detail, you will be able to figure out how many, what is the nature of this peptide. Okay, so now
this minus,
yeah.
there will be 4 residues or 5 residues.
This actually has four residues because this is the side chain. Side chain. Therefore, it has four residues unless there is an overlap here. See, these may be some overlap. That's what we saw here at this point. This point, there may be overlaps there. So these two peaks which are present, whether they are one residue or two residues, one doesn't know. Maybe they are two. So as we indicate here, this particular peak at 4 ppm and this 4 ppm is this fellow. This fellow. So this fellow is actually showing so many peaks there. So therefore, it probably has more than one. There's more than one amino acid. Yeah. So it is not a tetrapeptide. It is longer than that. Okay. Now here is this for the spin system identification. Once again, I have this amino acid site structures here, and this is the schematic of what sort of a correlations you will expect in the individual amino acids residues on the side chain. The histidine will produce a cross peak from 2H to 4H. And where is histidine? Let us look at histidine here. This is histidine. You will see a cross peak from here to here. That is this. This one to this one. So you will see that cross peak in this histidine. And tyrosine ring 28H and 35H. And tyrosine ring is, this is tyrosine, and you have these two will be equivalent, these two will be equivalent. So you will see a cross peak between these two. And that is this one here. 2,8 are equivalent, 3,5 are equivalent, 2,6 actually, not 2,8. Should be 2,6, no? 2,6. 2,6 and 3,5. The lettering is not very clear. And phenylalanine, you see where is the phenylalanine here? Let us look at phenylalanine. Here. So these two are equivalent, these two are equivalent, and this fellow will be separate. So there will be three groups. Phenylalanine is three groups: 2,6, 3,5, and 4. So you will have the connections from 3,5 to 4 and 4 to 2,6. So this will be in the COSY spectrum, but these empty ones are the ones which are said which will be there in the TOXI as well. So all of these will be present in the TOXI. The filled ones will be present in the COSY or the double counterfiltered COSY. And the tryptophan ring side chain, the tryptophan ring is here. So this has a proton here, the proton there. Okay, so they have three different protons there, and you will see those, and then you have proton here as well. But this fellow will stand alone. This has no connection. This proton will stand alone. That will be at 10.2 ppm, 10 ppm. The connections you will see only on those three protons. So, and those ones may be all be non-equivalent. So you have all of the 5 protons are shown indicated here, and
4 protons are there. There will be 4 protons.
There is one. Yeah, there is one here. There is 1, 2, 3, 4. 4 protons are there.
Maybe that is the NH proton.
This is the indole proton will appear at a much higher chemical shift.
What is the 2H?
2H.
2H is not connected to anyone.
2H will not be connected to anyone.
Just below the 6H. Just below the 6H.
6H. 2H is not connected to anyone.
Yeah. So that.
Yeah. So that is a singlet.
That is a singlet. That is coming from a different part.
That's coming from a different part. Yes, that's right. So this is.
It's probably that NH alpha to NH1.
This is the indole. There is a proton here and a proton there.
All 4 are there.
All 4 are there. So 4 protons, and 2H is where is that 2H coming from? It is not in the ring. It is not in the ring. What is the nomenclature here? This will be N9, isn't it? So 2 will be somewhere here. 2 is not connected to anybody. Singlet.
2 are all those 4 protons are connected to each other.
All others are connected to each other. Yes.
So that is probably that alpha to NH.
This may be the
indole aromatic.
AXMPA. This is written here. But where is the 2 position? The 2 position in the ring. 2 position in the ring is this one, no?
Yeah. So that will not be connected.
Yeah, that is that one.
Yeah.
This 2H is this one, this proton.
Yeah.
That is not connected to anyone. NH proton will appear at 10.2 ppm.
Yeah.
That indole will appear at 10.2 ppm. Okay. So the 2H is that. 2H is not connected to anyone. All other four are connected to themselves. Okay. So therefore you will have this sort of a structure in the kind of a tryptophan ring. And this is for the all other side chains which you have here. Table. This is all these are taken from Wittrick's book. Okay, for your information. This is taken from Kurt Wittrick. NMR of peptides, NMR of proteins and nucleic acids. And this is Wiley, 1986. So therefore, you see, you can refer to these various patterns which are given here. Individual. You see, when you sit down to analyze an NMR spectrum of a protein, all these correlations should be in the head. The side chain structure should be in the head. Every time you cannot open the book and see this, one must remember all these individual structures. It should be immediately on this. So you can immediately identify what is the side chain, how many peaks you should expect there. For the leucine, valine, which ones are methyl bearing residues, how many methyls are there, whether they will be equivalent, non-equivalent, what is the length of the side chain, does it go from alpha, beta, gamma, delta, epsilon, how far does it go? So all of these things one should be able to remember it very well. You will automatically get it once you dig into it. Once you are jumping into that field, starting analyzing, you will automatically get that info. Now this is for the other 7 amino acid residues, 4 plus 4, 8 amino acid residues here. The serine, aspartate, asparagine, cysteine, tryptophan, phenylalanine, tyrosine, and histidine. And here you have the histidine, you see it can have a charge there. And the chemical shift for this, all of these are also called ABX kind of systems. That is because it has the ABX means A is for the alpha and you have the 2 betas are non-equivalent typically. And 2 betas non-equivalent, you will produce, these are called as the ABX kind of systems. So therefore you see here alpha, the beta 1 and beta 2, and they see correlations between them. You see alpha to the beta 1 and beta 2, beta 1 to the beta 2, you will see cross peak here. This is the correlation. So normally, when you are analyzing your spectra, you group your peak patterns into different types, whether it is the ABX systems or the long side chain systems or methyl bearing systems. You classify your various peaks connections into that first. And accordingly, you start analyzing that, okay, this belongs to this group, this belongs to this group. Subsequently, with the knowledge of the sequence of the amino acid, sequence of the peptide, you will be able to identify through the nosy. When you go to the nosy, then you will find sequential connection from one residue to another residue. Now, there are other, these are long side chain amino acids, which will have, these are lysine, arginine, methionine, glutamine, glutamate, and proline. And these have many side chains, many peaks in the side chains. You see, they all go, therefore they called long side chain. They go from alpha, beta, gamma, and delta, epsilon. Up to that it will go. And all of them are indicated here, and their chemical shifts are also already indicated to you. So you see the pattern of cross peaks therefore is also like that. You will from alpha to the beta, beta to the gammas, and gammas you will not see from alpha to the gammas by and large. If there is in the toxic spectrum, you might see sometimes, you may not see it. But these cross peaks which are there indicated here. So alpha to the 2 betas, and the 2 betas will have peaks within themselves. And from the betas, 2 betas, you will see to the gammas here, gamma 1 and gamma 2. Okay, so there are 2 gammas, gamma 1 and gamma 2. The 2 betas to the 2 gammas you will have there. And then between the 2 gammas, you will also have this peak. This is gamma 1 and gamma 2 beta proton. Just as this one, you will also have gamma 1 and gamma 2. And this is for the glutamine, glutamate, and methionine. And proline and arginine, you will see from alpha to the 2 betas. These are here. And between the 2 betas, you see this peak. Notice the gamma of proline is above the betas with regards to the chemical shifts. Whereas for these, the gammas are down compared to the beta sheet. Why? Because these ones have the either the glutamine or the CONH2 group, or has the COOH group, or the S. Methionine has a S, sulfur group. That's why this gamma is downfield compared to the betas. And whereas in proline and arginine and these ones, you will see the gamma is above the betas. And therefore, those cross peaks will appear on this side. So from alpha to the two betas, you will see beta 1 and beta 2, you will see. From the two betas, you can see to the gammas there. Typically, the two gammas may be equivalent in this case. And then from the gamma, you see also a peak to the delta proton. This range goes all the way up to the delta. And for the lysine, this is true for the proline and arginine. And for the lysine, there is also an epsilon CH2 group. So therefore, you go from the alpha to the two betas here, and to the two betas, you go to the gamma. The two gammas may be equivalent, and likewise the two deltas may be equivalent. So from the gamma to the delta, you go there, and from gamma, the beta to the gamma is this, gamma to the delta is this, and then from delta, where is the delta? From delta, you see to the methyl. Epsilon CH2. From the delta, you see to the epsilon CH2 group. And in the same way, we saw earlier, the site CH2 is attached to a NH2 group in the lysine. That NH2 is the side chain. So you will see direct correlation from the NH2 also to the CH2 in the toxic spectrum or in the cozy spectrum. So the epsilon CH2 chemical shift is very distinct, and the side chain NH2 positions are also very distinct. Therefore, it is very easy to identify the NH2 to the CH2 correlation in the case of the lysines and in the arginines. Okay, now after this, we come to the analysis of the Nosy spectrum. This is so far as this is all within the amino acid residues. What sort of correlations you expect? These are J coupling correlations. Now we see dipolar coupling correlations. Dipolar coupling correlations are reflected in the Nosy spectrum. And if you see the Nosy spectrum, so again, let's look at this. Here you have the residue number I, NHC alpha CO, NHC alpha CO, NHC alpha CO, NHC alpha CO. So about four residues we are considering here. I plus 1, I plus 2, I plus 3. Okay. Now, depending upon the secondary structure of your molecule, you will have different kinds of correlations possible. If it is an alpha helix or if it is a 310 helix or it is a beta structure, antiparallel beta, or it is a parallel beta sheet, or it is a turn 1 or a turn 2. Depending upon the nature of the secondary structure, you will have different kinds of short distances between the protons. And those distances are indicated here. You have directly alpha N. This is alpha proton to the amide proton. This is alpha proton to the amide proton of the I plus 2 residue. This is alpha proton to the amide proton of I plus 3 residue. Likewise, alpha proton to the amide proton of I plus 4 residue. See, and this is the NNN, that is amide-amide resonance, amide-amide correlations. Remember, these are all inter-residue correlations, inter-residue. Whatever is intra-residue, you will see them anyway. You will, just as you see them in the cozy, you will see them here also. What is listed here as the inter-residue. For one residue to another residue, what kind of short distances you will get here. So here you have alpha D NN, then NNII plus 2, that is amide of residue I to amide of residue I plus 2. And this is the beta to the N, the beta proton to the amide proton, beta proton to the amide proton. So here it is alpha proton to the beta proton of I plus 3 residue, I plus 3 residue. When there is nothing indicated, this is actually the I plus 1 residue. Okay, so this is NN means these are the neighboring ones, I to I plus 1 or I to I minus 1, both are possible there. Okay, in this NN residue, because it goes in both directions. And that is typically indicated here. The NN is indicated here. This is NHI plus 1 to I. It can also go to the I minus 1 similarly. And therefore, NN connectivity has no directionality. You can walk along the chain. Whereas the other residues which are there, you see the distances are very different. All the distances which are there, typically, if there is a distance which is less than 3.5 angstroms, you will see a cross peak. And therefore, those are listed here. All the distances which are less than about 4.5 angstroms, they are all listed here. You expect to see cross peaks for all of these kind of things which are indicated for the different structures of secondary structures of the peptides. Considering a 4 residue stretch, you can see what all kind of a cross peak we can expect in a peptide structure in the Nosy spectrum. Of course, one has to record a Nosy spectrum properly with a reasonable mixing time so that you see all of those peaks. But given all of that, assuming that you optimize the experiment properly, you have all the correlations which are possible, then you see these kind of distances. You notice here, these are very short distances, and this is the alpha n. Alpha n distance is NH proton to the alpha proton of the previous residue. Okay, this is NH alpha n. This is the alpha n residue. This is very short in beta sheets, but this is not short in the helices. In the helices, it is 3.5 and 3.4. So therefore, in the NH alpha region, which is very strongly seen in the toxic spectrum or the COSY spectrum, you will see for the beta, you will see very strong correlations for the betas. You may not see so much in the case of alpha helices, but the betas, you will see them very well. Similarly, if you have an alpha helix structure, you see these distances are very short, 2.8 and 2.6. NH-NH correlations will be very strong in the case of alpha helices. NH alpha correlations will be very strong in the case of beta sheets. These are two very distinguishing features. Okay, that is the first level of identification you do. After that, you also identify other long range distances here. These are not too long range, but reasonably long range. The 3 residues further and 4 residues further, you will see this sort of correlations between the nearby residues. Okay. And that is again for the same thing what we took here. You see these correlations in the nosy spectrum. What sort of correlations you are getting there? So you have this same peaks here. 7.5 ppm. This is 7.5 ppm. Is it the same region or not? I'm just thinking.
Yes, sir, I think.
Same region, 8.5. 4. This is looking somewhat different here. There are two, see, each one of them has 2 peaks, we can see. Each line has 2 peaks. Okay, so this one is this, and this is the sequential peak in the nosy spectrum. This one is this is the sequential peak. This is the nosy spectrum because this is the NH alpha area. We are talking about N alpha proton to the amide proton of the next residue. That is the one what you are seeing. You see here the sequential peak is so strong. The self peak is weaker. The NHC alpha distance is in the beta sheet is about 3.5 angstroms. Whereas the sequential peak is 2.7 and 2.4 angstroms. Therefore, this peak is much stronger. The sequential peak is much stronger. And in this case, again, see, therefore, this fellow is this, and it shows a cross peak to this. So now you see, you can make a connection. I can draw the connections here. It's very easy to see it here. Go from here to here, here to here, here to here, here to here, then here to here. Then you also have connection from this one, here to here, here to here. Then you have a connection from here to here, and then it goes further. And this one is showing correlation to these as well. So therefore, you can make sequential connections from one residue to another residue. What are these? This, if I call this as a residue I, if I call this as a residue I, this will be residue I minus 1. And then this will be residue I plus 1. And this is residue I. Okay, if this is I minus 1, this is the residue I minus 1, right? Connection I to I minus 1, I minus 1, no, 1 minute. I plus 1 to I to I minus 1, this is NH to I minus 1, and I minus 1 to I minus 2, this must go to I minus 2. Of course, there is no corresponding one, where it is, we don't know. Okay, now this is a separate one now. This is a separate set of connections there. One could have drawn another way here. Suppose I want to take the same structure. Let me remove this. I'm just showing you how to analyze this. Let me remove this and I will draw once more a different kind of a connection pattern. Okay, so I say I go from here to here, here to here, here to here, then I go from here to here. I will not go there. Then I come here, then I go there, then I go there, then I go there, then I go here. All are connected. See the sequential connection, how you do. From the nosy spectrum, you are making sequential connections. I to I minus 1, I minus 1 to I minus 2, I minus 2 to I minus 3, I minus 3 to I minus 4, I minus 4 to I minus 5. So you got this connections in this. You can therefore walk along the polypeptide chain making use of this. Now, what is this individual amino acid residue? You can identify it from this, from the side chains. They also see correlation to the side chains. Therefore, you look at this and identify what sort of a residue this must be. Of course, this one is a standalone peak. We said this belongs to the epsilon of the lysine, and that is a standalone. That does not connect to any of these NHC alphas. So it is a standalone fellow. And therefore, this is not a part of the backbone. It's not part of the backbone. That is belongs to the side chain. And all of these are within the backbone, and this connects to the two betas. Okay, what this is likely to be? Beta 1 and beta 2 here, and this is very likely to be the one of the aromatic rings. So what is the chemical shift there? Say 3.0 to 3.2. So in that area, so it is very likely it is an aromatic proton. Similarly, this will also may be an aromatic proton, quite close there in that area. See, what you are seeing here, the connection which you go from here to here, here to here, right? The same connection you see from here to here and here to here. It's the same connection. So from NH to the betas and the betas to the beta. Just as you walk from in the alpha area, NH to the alpha, you can also walk in the beta area. So all these are confirm your analysis, how you walk along the polypeptide chain. Now, so this is a typical pattern which is shown here as already indicated to you through the experimental spectrum, the connection patterns which are there. You start from here, one particular residue. This is the residue number 5 to, what is the number there? Oh, 1, this is 1. Okay, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 is ending there. So this is how you walk on in the sequence, and that is indicated here. So this is I minus 1. This is only through 3 residues which is shown. But this is the typical walking pattern in the NH to the alpha area. And if we are in a helical area, you see, notice there is a diagonal here, which means what are we talking about? We are talking about the amide region here. The amide region, I told you in the alpha helix, this is in the beta sheet. This is the beta sheet. You will see such kind of connections in the beta sheets, very prominent connections in the beta sheet. Okay, and this is the helix here. In the helix, what are the prominent connections? NN connections. That is amide to the amide of one residue to the next residue. So therefore, you see, if you have an amide, every amide will show you 2 peaks. One to the previous one, one to the following one. So therefore, whereas there is a directionality in the NH alpha NH area, that is coming in this area, there is no directionality here. You can walk along both sides in this one. Let's say you take the same one there. So you take one here. So this one is showing a peak to this. Okay, now it is also showing to this here. You see 2 peaks from there. That is the same thing which is taking here. 1 to 2, 2 to 3, 3 to 4, 4 to 5. And these are NH-NH connections. If you have the beta sheet, if the helical area, if the same stretch is in the helical area, then you will see this kind of a correlations there. It is not that such correlations will not be present in the helix. They will also be present. They can also be present there. But it will be more prominent in the case of a beta sheet. But in the other cases, they can be weak. They can be weaker there. And this is typical, this is a summary of all of that what I showed you, which is indicated here. You consider the long stretch of 6 amino acid residues, what all connections you will see from one residue to another residue. These are 1 to 4 residue, 1 to 3 residue, I to I plus 3, I to I plus 2, I to I plus 2. And then these are the neighboring ones, alpha n, also neighboring ones. And this is indicating the coupling constants here. What sort of coupling constants you will have in the case of different NH alpha couplings, 3-bond NH alpha couplings. So typically one has to depict your nosy analysis in this manner. If you are concluding that you have an alpha helix, you should show a stretch of connections like this. Okay, you should show this, you should show this, you should show this. All of these one has to show to confirm that what you are determining is the alpha helix. If you are having a 310 helix in your structure, then you should show this, show this, show this, and show this. And of course, show this. Same here as well. Okay. And for the beta sheets, you will see three NN connections, alpha N connection. Yeah, that's what I was looking. Alpha, this is so powerful. Look here. For the betas, this one is so strong. The thickness of the bar indicates the intensity of the cross peak. How strong the cross peak will be. Accordingly, the thickness of the bars are different. Okay, but they will be present. So you will have to identify those. According to the thickness of the bar, it should match the pattern what you expect here. For the alpha helices, for the 310 helices, turn 1, turn 2, turn 1 prime, turn 2 prime. These are finest details of that one. And there are certain half terms are also. They are typical secondary structure elements. So overview or sequential and medium proton NOEs and spin coupling constants. This is another thing. Spin coupling constants are measurable from the Cozy spectrum, double quantum filtered Cozy, but you will have to simulate this because these ones are very fine structure. There are many components in each one of those. To extract the coupling constants from there, either you have to do a 2D J-resolved experiment, or you can do high resolution Cozy, double quantum filtered Cozy, and analyze the fine structures in those. That is, or you can do J-scale Cozy experiment, or the or the constant time Cozy experiment. All of those things will help you to measure the coupling constants. The coupling constants also will vary depending upon the secondary structure what you have. See here, for the HN alpha, these coupling constants are very large. For the beta, NH alpha coupling is very large. This is about 9 hertz. And if you go to helix, that coupling constant becomes 4 hertz. And similarly, in 310 helix, it is also about 4 hertz. Turn 1, you will have one 4 hertz, another one 9 hertz. And your turn 2, 4 hertz and 5 hertz. And 7, 5, 7, so on, so forth. So this data is there. You have to analyze all of these things there. Okay, I think I've finished here. So this is how you analyze the peptide structures, peptide assignments and peptide structures. Protein structures go a little bit beyond this. Of course, you will have to use heteronuclear and all other kinds of multidimensional NMR experiments to get to the structures of the proteins. That will form a topic for the next module. So with that, we will stop here. Now, if you have any questions of any type, either for today's lecture or from the previous lectures, you can ask.
Any question from this
Any
or
question like that? Any doubt?
doubt from this lecture and earlier lectures?
Any doubt is good enough. And maybe
So coupling constants are also will be indicator of that will also give a first an indication that
About the structure, secondary structure. Alpha helices will have very low coupling constants.
because the current line is, yeah, it is becoming very close to 90.
Yeah, yeah.
So then correlate with nosy.
Then you correlate with nosy. Yeah.
So this pentapeptide, hexapeptide, you prefer nosy or rosy? Which would be better?
Rosy will be better. See, because sometimes there is a risk that you may not see. Yes.
certainly no question coming. But sir, you can announce this way. If any doubt, they can write to.
So if you have any doubt, you can also write in mail, and so we can address those questions.
Yeah.
Mail's address is already there in the. They can write to you.
Yeah. You must go through all the PowerPoint files in detail so that you try and understand that. Because if you don't study now, if you don't understand it now, you will never understand it.
And also they can write this any doubts in the help desk also.
Yeah.
Or wherever solve
It is
question.
given already.
Correct, correct.
Address is given, so they can write. And they can write directly to the professor.
Yeah,
And
so no, it is better if you write here so that it can be.
Assignments of all these topics.
Yeah. Assignment also, we gave 20.
20.
Date I forgot actually. Okay, participants, so try to send your assignment, solve this and send it as quickly as possible. Okay?
सबका भी assignment दिया था क्या?
Yeah, two assignments are given, two from Professor Ghosh and two from Professor Husser. So there are 4 assignments for you this course.
Okay, and now next week the exam. Okay, after my course is over, nahi, abhi there you want 2 more, I will give one more assignment.
So rest of this part 1 course will be taken by Professor Ghosh and we will start from next week.
Okay, I think they will not have any doubts, so
Now I think let them go through the
yeah.
literature. Because all notes are given already, so they should go through
So they
it.
should study them, they should study them.
They should study them.
You send these also.
Right, study the notes and come up with the doubts directly with Professor Beckerland.
Right, that.
Notes, all notes are available in Unuvik.
So.
One more line you write, submit assignments by next Friday. Is it okay, no, boss? By next Friday.
Now minimum 2 weeks the.
Already 2 is over,
Okay.
so next Friday is.
Submit all the assignments, yes.
By, not till, by
Next weekend.
next weekend. Assignment is करो. Assignments.
Maybe assignments.
Yeah.
Okay, then we can.
Okay, so then we close here.
Yeah.
Okay. Wish you all the best.